Titled Audio for Kinect, From Idea to Xbox Play. My name is Ivan Tashev, and I'm a principal architect in Microsoft Research in Redmond, Washington. If during this talk you start to feel like you're in school, your feeling is right. I spent one half of my career as a university professor. The good thing is that you won't have to take exam on the content of the talk, so just relax. During the talk, I'll play some loud sounds just to wake you up so you don't fall asleep. But overall, we're going to talk about Kinect and its audio part. We'll start with describing what is Kinect from a little bit different standpoint. Kinect as a sensor for doing human-machine interface. And then we'll talk about the audio pipeline and what we have for the sound capturing in Kinect, what we do and how we process it, not targeting you guys at some point trying to write something like this, but more to know what are the capabilities of this audio pipeline and what scenarios it enables. This is why the second part of this talk is called Voice-Enabled User Interfaces, and we'll talk in general what speech and speech recognition can bring to building a nice and cool and intuitive human-machine interfaces. And this is not just about Kinect. This is about mobile phones. This is about in-car applications, what we can have if we have a good sound capturing part. And we'll discuss some of the major achievements in the Kinect audio pipeline and what we can do further. But before to start, okay. Let's start with describing what Kinect is. The picture is not accidental here. 5-10 years ago, when you say computer games or game consoles, what we see is an imagine is two young males holding those controllers and hectically pushing the buttons, trying to kill the bad guys on the screen. And that was pretty much most of the gaming. We'll discuss what new thing Kinect open it. But before that, let me tell you a couple of words about Microsoft Research, the organization I came from. So it is created exactly 20 years ago in 1991 and is the second largest research organization in computer science in the world. We have 6 labs spread worldwide. The major is in Redmond, Washington, the headquarters of Microsoft, but we have branches in Cambridge, UK, in Beijing, in China, and several other labs which are with smaller size. Microsoft Research has more than 850 researchers. We do research in 555 areas of the computer science, computer graphics, human-machine interfaces. It's a very academic organization. We so far published 3,500 papers on the first-tier conferences. Microsoft researchers submitted more than 2,000 patents. This is the technological brain trust of Microsoft. There is not a single product of the major products which Microsoft shipped without algorithms and technologies designed by Microsoft researchers. But still, I want to underline here, because this talk will be mostly what you can do, not what Microsoft delivers as a product. In Microsoft Research, we in general do not ship products. We do not deliver anything to you directly. We deliver through our business groups. We work with our product teams, give them the best technologies we could design, they deliver to you. And there is one pleasant exception, actually. This is Kinect for Windows Development Kit, which will be delivered for non-commercial purposes. How our Chief Strategy Officer promised by the end of the spring. Astronomically, spring ends in midnight, June 20th, just to remind you. So, Kinect. Everybody, I believe, have seen the device. If you haven't, there is one of them. And what we have here. Kinect in general contains 3 sensors. One of them is the depth camera. The camera which converts and looks like a black and white image, but each pixel, instead of brightness, encodes the distance. And once we have the distance, this allows us relatively easy to remove the background, to do classification of the pixels of the human body, and pretty much to assign coordinates in 3 dimensions, x, y, z, of every single joint of the human body, which means to get the green silhouette on the screen, and each of those dots is a major joint, and the game developer gets x, y, z of those. There is a regular camera, regular RGB camera, and there are 4 microphones which form so-called microphone array. So you understand that once we have the depth image, this is relatively easy to convert to this skeletal tracking thing. And once the game developer has its X, Y, Z's of the major joints, then gesture recognition is, okay, piece of cake, roughly speaking, but technically means if Z of this joint is bigger than Z of this joint, I have a hand raise. If the Euclidean distance between this joint and this joint is closer than something, I have a clap. So this is how simple it is in the user layer in the gaming code. But of course, this talk is not about gesture recognition and the modality gestures bring to our user interfaces. This talk is about audio. So let's see what we have in Kinect, which allows us to do sound capturing. What are the challenges, the problems we have to overcome? So happened that the major problem in audio for Kinect is the sound from the loudspeakers, by several reasons. First, gamers tend to listen to very loud sounds, some of them on the threshold of pain. Second, the device is very close to the loudspeakers. So you can imagine your 5.1 surround sound system, and you have 3 loudspeakers in front, center, left, and right, and the device is right there. Which technically means that even if the center loudspeaker has the same loudness as my voice, but it is positioned at 10 centimeters from the Kinect device, and I'm 4 meters away, the Kinect device will hear the sound from the loudspeaker 40 times louder than my own voice. So this is one of the things which we have to overcome. We want to be able to send voice commands to the system even when the loudspeakers are playing with basically very loud sounds during game, during watching a movie. The second is the reverberation in the room. When we speak, besides the direct path from the mouth to the ear, multiple delayed and attenuated copies, reflections from the walls, from the floor, from the ceiling, reach the ear with certain delay. And this leads to smearing of the speech features, which makes the speech recognition way more difficult. And of course, there is the noise in the room, which is comparable as level to a human talking from 4 meters, pretty much the distance we want to capture the human voice. So this means that the noise which comes from the TV, the Xbox, the air conditioning, some additional noises from the street, that basically very, very low level is the same as the level of a human voice from 4 meters. We humans do not hear this thing because we have 2 microphones and 100 billion neurons between them. Humans have amazing ability to filter the noises, to focus to the sound source, to listen and to understand speech. And of course, in this particular case for Kinect, we have enormous dynamic range. Remember, speakers are near, they are playing very loud sound, and we want to capture a chilled voice 4 meters away. So we have to handle this somehow, this enormous amount, the difference between the levels of the sounds. And of course, as you will see later, even when you have a set of nice and cool audio processing blocks, each one of them optimal, what is going to happen is that when you put them into a one audio processing chain, they are suboptimal. So you'll have to take care and to build the end-to-end system. Never ever to lose the look of from the microphone to the speech recognizer output. So what we have in Kinect? Here is kind of a rough block diagram of the audio pipeline, which does speech enhancement and audio processing in Kinect. And what we have at the beginning is block called constant tones removal. Those are the sounds which the device captures from the TV sets usually. The frame and line frequencies, which with their harmonics actually cover the entire audible diapason. Then came a block called multi-channel acoustic echo cancellation. This block has the main purpose to remove the sounds we know about, the sounds we send to the loudspeakers. And we'll talk about this a little bit later. And next is so-called beamformer, combined with sound source localizer, which converts Kinect device into a highly directional microphone, pointing towards the sound source, and we need the sound source localizer to know where to point this highly directional microphone. And after a couple of blocks, which we're not going to discuss today, which is called acoustic echo suppressor, noise suppressor, and automatic gain control, which allows to bring the same output voice level regardless how far you are, regardless how loud is your voice. So happened that for the scenarios we want to solve with the Kinect device, two of the blocks play a major role. One of them is the multi-channel acoustic echo cancellation, and the other is the microphone array support, the beamformer, and this is why we'll take a little bit closer look to them. So acoustic echo cancellation and acoustic echo reduction is most probably the oldest and the most developed algorithm in audio signal processing. Pretty much it is part of every single speakerphone. What we try to do is to remove the sound of the loudspeakers captured by the microphones. If we do not do this, what is going to happen in the case of the communication line, two telephones connected together, is when we speak, the microphone will capture our voice, we will send it through the communication line, it will play it by the loudspeakers on the other room, captured by their microphones, return it back to us, played by our loudspeakers. In the best case, you will hear annoying echoes, like a cave. In the worst case, we even can have a feedback, which means having a generation of a constant tone. You have heard those annoying sounds from time to time when the audio system in a room does not work quite properly. So the idea is following. If we can estimate what portion of the loudspeaker signal is captured by the microphone, this is capital H here. If you can estimate this function and then filter the loudspeaker signal with the same function, and you subtract it, technically right here on the output we will have just the local sounds, the noise, and the local speech. Because we cannot do this quite precisely, there is a so-called residual y of k, and we need a small additional block to do additional suppression of the sound from the loudspeakers. Okay, but in Kinect we do not deal with mono sound as in the communication systems. In Kinect we deal with stereo and surround sound. And this is way more complex to solve than just the mono sound. The most intuitive thing is to say, okay, we have two channels. We can chain two acoustic echo cancelers to subtract the signal from the left loudspeaker, then to subtract the signal from the right loudspeaker, and at the end, we will get the sound from the loudspeakers removed. This thing does not happen in real practice, because in most of the cases, we have the same sound. Imagine the sound synthesis system of the game which wants to synthesize a moving sound source. And when we have one sound source, pretty much the two last stereo channels, they have a delayed and attenuated copy. So pretty much if you have two loudspeakers and want the human to perceive a moving sound source like this, we will have the same sound, first louder on the right speaker, and then slightly the loudness will gradually move to the right speaker with proper delays. And because those two signals are pretty much the same, we cannot solve the system. Think about purely mathematically. We have two unknowns: the transfer function between the left speaker and the microphone, and the transfer function between the right speaker and the microphone. And we have one equation, which is the microphone output. This is why this system cannot be solved, and it is a long-standing research problem. Even the inventor of the acoustic echo cancellation himself, in 1991, published a paper mathematically proving why this is not theoretically possible. So now the question is, can we reduce the number of equations from 2 to 1 to be equal of the number of the microphone channels? And this is why in Kinect we use this architecture. What we want to do is initially to estimate the initial transfer functions between the speakers and the microphone, and then just to have a small adaptive filter here to compensate for people moving in the room, doors open, close, etc., etc. To estimate the initial calibration pulses, to initial functions, we have so-called calibration, which is a surround sound or stereo acoustic echo cancellation specific, and I will play some familiar sounds here. So this is supposed to be rendered through 5 channels on your surround sound system, and it sounds very musical, but this music contains every single frequency between 200 and 7,500 hertz, so we can estimate the transfer function for each of the frequencies. And once we do this during the calibration, we store those transfer functions and then let the adaptive filter to compensate for the changes in the temperature, somebody moving, etc., etc. In Kinect, this is implemented, this architecture is implemented for 5 channels surround sound and all 4 microphones. Bottom line here, do not forget to calibrate your Kinect device, otherwise you will not get a good reduction of the sound from the loudspeakers. So going further, presumably we removed the sound from the loudspeakers. Now what we have to deal with is sounds and noises we don't know about, the noises in the room. And to deal with this, we use so-called array processing technology or multiple microphones. This is not something new invented for Kinect device. Array processing technologies are used from a long time for focusing and listening towards given direction using multiple sensors. In this room, looking around, I see one array of radio antennas right there. That white circular thing contains multiple antennas and try to focus. This is the Wi-Fi access point, and it tries to focus on each of the laptops which is online, so they have a better access to Wi-Fi. What is important here is that we can combine the signals from the 4 microphones in a way to make this guy to listen towards given direction. Because sound will reach the microphones in a different order when someone speaks. For example, if this is our microphone array, by the way, the microphones are underneath. You can see them if you look at your Kinect device. What happens is that if the sound comes from this direction, it will reach the microphones in certain order, which is delayed, the same signal. But if the sound comes from different direction, the order will be different. The most intuitive thing we can do is to align properly the signals from the microphones arriving from the direction we want into a way that when we sum them, to have a constructive interference, which means they to sum E. And if in this case a sound comes from another direction, they will be not properly aligned in a different phase and you'll start to cancel each other. And this process of summing in a proper way of signals is called beamforming because it forms a beam, a way to listen towards given direction and suppressing the sounds coming from other directions. And because everything happens using digital signal processing, if we change the way we mix those four signals, we can make this beam to move. So this is called beam steering. And this is exactly what happens in Kinect. If you guys have seen when people shoot movies, there is a sound operator, a person who usually holds on a long stick, this long microphone, and points towards the artist who is talking. So this is exactly what Kinect does, but completely automated. So we have this directional microphone beam, and the sound source localizer tells us where the sound source is, and we steer the beam towards the direction we want to listen to. And of course, we can do even more here. If you know that there is a person A, and we want to capture this voice, and there is a person B speaking in the same room, and we don't want to capture that voice, we can enforce so-called null, means suppress completely the sounds coming from that direction. And we eventually, if that person moves, we can steer this null. So in general, to get the sound we want as much as possible. And let me show some charts here. In the upper right corner, you have a so-called directivity pattern of the microphone array of Kinect. Where is my cursor? Okay. So this is the direction. And this is frequency. You see that this microphone array actually points towards 0 degrees, and it suppresses quite well sounds coming from other directions, which is exactly what we want. In Kinect, we use so-called adaptive beamformers. They actively try to see, do we have additional sources than the one we want, and to suppress them. And in the second case, the chart in the lower right corner, we have exactly this case. We have a person speaking at 20-something degrees right here, this direction, which we want to capture. And there is one more guy at -9 degrees right here, we don't want to capture. And you see how the beamformer automatically adjusted the directivity patterns in a way that the person which we don't want is completely suppressed, and we still have a unit gain and zero phase distortions towards the direction we want to see, or to hear. So now I'm going to show you two demos. The first is just to demonstrate the sound source localizer and how it works and how it can track 1, 2, 3, testing. So I can move 1, 2, 3, 1, 2, 3, 1, 2, 3. I'm hoping that my voice is dominant there and not the voice from the loudspeakers, but as you can see, 1, 2, 3, testing, 1, 2, 3, 1, 2, 3, it can, in general, do the sound source localization, and the green is actually the directivity pattern of the beam pointed towards me. So this is a demonstration of the sound source localizer. The next thing I'm going to do is to do a recording in parallel with a single microphone, which is one of the microphone of my laptop and the Kinect device, and we'll be able to compare the output of those two. And I will try to switch off the microphone for this demo. One, two, three, testing, parallel recording. One, two, three, testing, parallel recording. So a couple of things here. First, my guess is that none of you guessed that there is so much noise in this room. Remember, we have 100 billion neurons, and by the way, a microphone array, 2 microphones. So we can do the same, and we are doing it. Actually, way better than our audio processing chain. Second thing, if you listen to my voice, the second recording sounds that I'm closer because it contains less reverberation. The beam, which is narrow, focused towards me, removes the noise coming from other directions, but also removes the reflections from partially, reflections from the wall and the ceiling. And because of that, it contains less reverberation. And humans subconsciously judge the distance by the amount of reverberation. Means more reverberation, the sound source is further away. Less reverberation, it is close. So pretty much the more directive microphone, which the beamformer is, actually brings the persons closer, reduces the reverberation and all negative effects of it, and reduces a lot of noise. If you can see the numbers here, the single microphone had signal to noise ratio around 13 dB, and the output of the beamformer had 36 dB. So we get around 23 dB noise suppression just in this particular case here. So obviously the audio processing chain is way more complex than the simplified block diagram I show it and I show here. And the only purpose of this block diagram is to show how the system works end to end. So I will play you a real recording, pretty much on the verge of abilities of our system to clean up sounds. And the first recording will be what one of the microphones hears, and the second will be the output of the audio pipeline. During the first recording, besides the sounds from the loudspeakers, we have a person staying in the room and reading voice commands to Xbox. So let's listen to the first recording.
Xbox shuffle.
Take a deep breath.
Any guesses about the commands? So let's hear the output.
Xbox shuffle. Xbox dashboard. Xbox go back. Xbox next level.
So this is a corner case, pretty much on the brink of our abilities to clean up the signal and to bring something to the speech recognizer. In normal conditions, with the levels of the sound from the loudspeakers normal people listen to, it actually is way better than what we just heard. But still we are able to reduce and to remove a lot from the noise from the loudspeakers and from the ambient surrounding us noise. And one more thing I want to share with you is when you build, which actually can be used by you as well, is that when you build a system which contains a set of blocks, they are optimal mathematically, but as a result, the chain is not optimal mathematically. And there are a lot of parameters inside those audio processing chains, like thresholds, time constants to update noise models, et cetera, which is kind of hard to estimate. And this is why we look at and ask it, okay, what we want to achieve. What we want to achieve is humans to perceive the sound on the output as the best possible quality, and the speech recognizer to be able to recognize as many words as possible. There are competitive measures for this. For the sound quality, it is called MOS, Mean Opinion Score. It's ITU-T standard, the International Telecommunication Union, and it simply means you go and ask 50 people to listen to those recordings, and each one gives a rank from 1 to 5, then you average. So this apparently is kind of time-consuming. There is a computational proxy of this algorithm called PESC, which is called, it's the abbreviation for perceptual evaluation of sound quality. And this is already something we can use because it takes the audio output and gives us a number between 1 and 5, pretty much as good as 30, 50 people average it. So then it's kind of simple. You take those things to adjust, 75 parameters across the entire audio pipeline. You put it somewhere to process, let's say, 50, 60, 70 audio recordings with various levels of the human voice, the loudspeakers, various content, different gender, different age, et cetera, et cetera. This is the model of the real world. And now the question is, can you tweak those 75 parameters in a way to maximize the perceptual evaluation of sound quality and to minimize the word error rate? So this is a classic algorithm for mathematical optimization. What can stop us to do it is that it requires a lot of computations. So for this, we use one of the clusters in Microsoft Research, 256 CPUs, which worked day and night for 48 hours before to produce the final result. I'll show you just this simple chart. On the horizontal axis, here we have the relative loudness. Pretty much the volume control of your amplifier can be basically put between 0 and 100%. And on the vertical scale, we have the word error rate. So how many words were wrongly recognized by the speech recognizer. The black is just a single microphone. And there are two red lines. One of them shows up to where, the vertical one, we want to work. That's a little bit above reasonably loud sound from the loudspeakers. And we have to achieve a word error rate below the horizontal line, so we can say, okay, this is already enough good to build a voice-enabled dialogue system. So what we can see is that the black line does not meet any criteria for shipping, and under any circumstances, we cannot achieve a reasonable quality. When we put those blocks together, before to start the optimization of the audio pipeline, this is the red line. Okay, for certain low level of the loudspeaker levels, we are meeting the shipping criteria, but not quite. After the optimization, this is the blue line, we kind of put the word error rate down. And after retraining the speech recognizer itself, which is the green line, we finally met the shipping criteria. This happened on September 26th last year. As you can remember, Kinect was shipped on November 4th. Okay, why we're doing this? Why we need sound from the media room? What is the purpose of this audio? The purpose is that we can build speech-enabled user interfaces. Interfaces which are multimodal, they have a lot of components, and one of them is human speech. That we can allow the user to say what they want and to get the computer to execute the command. So behind this formula in the middle, which is a generic description of what the speech recognizer does, it's just a probabilistic machine which, given sound sequence S, tries to estimate what is the sequence of words. And it can be split relatively easy using the Bayesian rule on two pieces. The first is so-called language model. This is the prior probability, what is the probability we to have this word in this particular sequence. And the second is how similar is the sound sequence to this particular word. So one of them is called language model, and the other is called acoustical model. When I said retraining of the speech recognizer a couple of minutes ago, I meant training of the acoustical model. This happens on a cluster of more than 1,000 machines and takes around 1 week. So that is something which we don't touch. At least you as users, consumers of the speech recognizer, don't touch at all. The only thing you have to know is that you have to have acoustical model, train it on that set of sounds I want to use. The second, the language model is something which every single speech-enabled application jungles constantly, changes constantly the language model. And there are two ways to provide this language model, and the first one is called context-free grammar. So context-free grammar is pretty much a set of phrases we expect the user to say. Based on these phrases, we build the CFG, the context-free grammar, and feed the recognizer, which uses the acoustical model to recognize those phrases. It is actually just an XML file. And when you hear dial of a phone to a major company or want to book your tickets for the airplane, and when you hear the prompt, please say flight information, new reservation, existing reservation, or customer service, while the computer plays this prompt, it loads this XML file, which is down, and it just says that we expect the user to say either flight information, new reservation, existing reservation, or customer service. And even, you can see on the right, there are given probabilities that we expect the users to say that. This is very nice, but as you can see, it's very rigid. We do not allow the user to make even a step outside of the prescribed several phrases. And this is pretty much where the Kinect speech interface is today. You say Xbox, and you see on the screen several things get black background, white letters, and say, oh, this is what I can say at this moment. So this context-free grammar is actually quite good for menu selection, for fixes, several the decisions the speech recognizer should make. Is this a problem if you want to do something better than that? Let's say we want to select one of the 5,000 songs we have in our media player, or in our telephone, or in our computer. The problem here is that even with a very good speech recognizer, the human is the one which gives us problems and mistakes and ambiguous queries. Humans tend not to remember the exact name of the song, of the title. And more than 1/2 of the queries actually contain multiple fields. So it is very difficult to train users which play with their phone or sit relaxed in their media room to say exact structure of the command. For example, Xbox play song title. Okay. Or Xbox play title, song title. Xbox play artist, artist name. Besides making additional, they're not sure what exactly they want, and we can hear stuff like, play me that song about submarines by the Beatles. So pretty much we have wrong title, wrong structure, and actually we want to be able to help our customers to have this freedom, these free phrase queries, and plus especially in the symphonic music, the metadata, what we have as a title is in most of the cases enormously complex and you just cannot memorize it. And I have two examples here. Play track serenade number 13 for strings in G major, K525. That's the Little Night Music. And you even want, if the user says play Little Night Music by Beethoven, even if we want to play it, even if the song is, the serenade is written by Mozart. So we have to want to tolerate human mistakes as well. What we can do here? So then, because we cannot have better humans, we have to make a better user interfaces. And the way to do this is to change slightly the way we use the speech recognizer. So instead of having a rigid fixed phrases or fixed song titles and names, what we do is we ask, let's say, 100 or 500 users to ask for the music titles for the songs they have in their computers. We can even do a more massive data collection with some of the services we provide. And based on those phrases we compute so-called statistical language model, which is already first gives the probability the user can say every specific word and every series of 2 words and every series of 3 words, so-called n-grams, bigrams, and n-grams. And that already allows a little bit more freedom. And still, even if we recognize everything correctly, we have to deal with the user's ambiguous queries. And this is why after the speech recognizer, we have so-called spoken language understanding, which is a parser and tries to map whatever the user said to 1, 2, 3 more candidates. So this allows us actually to build a quite flexible and nice modality in our user interface. We can add speech, we can support not strict queries, fuzzy matching names. This minimizes the dialogue terms. And when we have an experienced user which knows what wants, we can have this user to say exact query, exact clarification. And if the user is not so skilled, we can basically try to help and to do it in several dialogue terms. But that's not everything. Speech is nice. But if we use only speech, this is the equivalent of telephone interface, telephone call. And this is not what we want. This is not what we have on our devices. On our devices, we have graphic screen. We have voice, we have touch, we can do gesture with Kinect. We have graphic user interface, we have sound, we have buttons. How to use each one of those multiple modalities to build a more intuitive, more user-friendly interface. And if this interface does not require training or reading the user's manual, then we can say that this is a natural user interface. So this simply means that we should use each one of those modalities where they're strong. For example, voice is very good when we have to search through long lists. Just think you have 3,000 songs in your mobile phone, and you have to do this 3,000 times. That's kind of unlikely. Or you can just say, play that song about submarines by the Beatles and get 3 or 4 candidates. Then, if now you have to listen to the text-to-speech engine to read the metadata of all of those 4 songs and you have to say play 1 or play 2, that's lame too. You just can't touch. So touch is very good when you have to select from short lists which fit on a screen. Speech is good when you have to select from large lists which cannot fit on the screen. Those two combined, only 2 of the modalities I just enumerated, and we have something quite useful and quite powerful. So this is pretty much the bottom of the bottom line of the multimodal user interface. You have a lot of means in your hands. When you design your application, the user interface of this application, try to use each of the modalities where it is stronger. That will guarantee that intuitiveness, easy to use, and preferred by the user's user interface. And now I'll give you an example of a multimodal user interface for in-car infotainment system, similar to what Microsoft ships to FordSync, Kia Uvo, and my guess is that you will say, wait a minute, this talk is about audio for Kinect. We're internet and mobile developers. They're showing us a demo with in-car application, which is embedded systems mostly. And the reason I do this is just try to get out of the scope of Kinect only, and just to show you how in a specific environment, you can make something nice and cool. Most of the approaches actually are applicable for any speech-enabled application. So let's listen to this. So my name is Ivan Tashev, and I'm Principal Architect in Speech Technology Group in Microsoft Research. We're in a driving simulator lab, and I'm going to demonstrate Commute UX. Commutex is a next generation in-car dialogue system which allows you to say anything anytime. This is a dialogue system which employs natural language input, and the system still will be able to understand you. Let's see how it works. At the beginning of our trip, let's start with listening to some music. Play track live for the party.
This is the life of the party. We gonna do it right.
So this was the classic way to listen to send a speech query, but we don't have to specify track or album or artist. Play Paul Simon. So as you can see, the system didn't need the clarification about the artist. Play The Submarine by the Beatles. And it can even understand not correctly specified names. Let's make some phone calls. My Bluetooth telephone is paired with the system, and the computer knows my address book, so I can ask directly by name. Call Jason Whitehorn.
Calling Jason A. Whitehorn, say yes or no.
Yes.
Jason A. Whitehorn, do you want cell, work or home?
Cell.
Calling Jason A. Whitehorn at cell.
So this was a classic and slightly painful way to interact with the Bluetooth phone, but our system can understand and doesn't need disambiguation if the name is unique. For example, call Konstantin at home.
Calling Konstantin Evangelos Lignos at home.
But there is even more. Frequently the driver needs to respond to some urgent text messages, and it's definitely not safe while you're driving. So we can use our speech input to do the same.
Message from one, ETA, say reply, delete, call back, or skip.
Reply. In 10 minutes.
Am I right that you want in 10 minutes? Or a number from the list?
Yes.
Got it. Message sent.
Maybe you notice it, but there is some irregularity in movement of our car, and I'm afraid that we have a flat tire. And because this is a rented car, I even don't know how to open the trunk. So now it's the time to open that thick car owner's manual and to try to figure this out. But instead of this, our computer already did this for us. So we can just ask how to open the trunk. And we see the proper page here. But then we need to replace the flat tire. How to replace a flat tire. And we go directly to the page of the owner's manual which describes how to replace the flat tire. Once we have our flat tire fixed, we can continue our trip and listen to some music. Play Norah Jones. We have a nice toys in Microsoft Research, right? Just to clarify, the speech-enabled voice interfaces still cannot replace your flat tire. You have to do this by yourself. But to summarize, so we saw 4 demos. Voice dialing, song selection, document browsing by voice, and SMS reply. All of those, they have the same technology behind. SLM and spoken language understanding unit. In all cases, it's a matching of what user said with a list of items on the right. In the first case, it was a list of a couple of thousand songs. In the case of SMS reply, especially for in-car environment, you cannot afford to do dictation. Speech recognizers make and will continue to make mistakes. Humans make mistakes. When you dictate to a human, a secretary, a message or a document, frequently she stops you and says, what was the last thing you said? So we have to provide a correction interface for our dictation interface, and this is a no-no for the car. So what we did actually is collected around 3,000 to 4,000 SMS messages for this particular domain. Drivers need to respond urgently with the SMS messages. Some of them are the last in their lives. Just kidding. And pretty much put them together, process it a little bit with so-called slots. So when you say in 10 minutes, 10 is a slot time, etc., etc. And this is pretty much what happens. When you say reply and dictate the text of the message, we try to extract the gist, the information it carries, and to match it with the closest, with the same meaning message. It may not be the same wording, and to show you to select the one of those four. So in summary, what we did, what we talked. So Kinect first. There are several serious achievements in Kinect audio. First, for the first time ever, a company ships a product with surround sound echo cancellation. Second, we are able, one of the first in the world, to capture and to provide enough good quality of speech from up to 4 meters. And the last thing is the first ever open microphone speech recognition system. You notice that during my in-car demo, I had to press a push-to-talk button to tell the system I'm talking to you. In Xbox, with Kinect, I have the voice equivalent of push-to-talk button. I have to say Xbox and then the command. One of the reasons this audio processing chain worked well is doing this end-to-end optimization. And I want to assure you, this is just the beginning. More and better, exciting, and more exciting technologies are on the pipeline, coming from Microsoft research towards the Xbox product team to provide a better and better service for better and better user interfaces. So summarizing, Kinect is nothing else but a human-machine interface device. And that device goes way beyond gaming. Actually, for me, it's way more compelling sitting on the couch just to be able to say which song I want, which movie I want to watch from Netflix. And actually, user studies with our beta program show that 54% of the users prefer speech as a modality for media consumption. And to summarize, multi-modal interfaces is when you use each of the modalities where it is stronger. And the last thing, just a glimpse of what we do and work on in Microsoft research. Of course, one of the major things is fusing the various sensors. Can you combine the vision, depth, and audio and to have a better results, to know more about the person standing in front of the device, so to guess properly what we can expect. And if you can get the gender and the age by the voice and the shape of the skeleton, and when this person asks for movies, most probably you should bump the priority of action movies. And especially if this is the owner and we have the previous history of his movie searches. And by the way, suddenly if we see unknown and unregistered into the game console database, a young female, maybe you should bump the probability of the romantic movies because it's a different moment in the life of the owner of that game console. So anyway, I will do one demonstration here. It is called sound source separation. We have two persons, 2.4 meters away, 26 degrees separation. This means they are standing shoulder by shoulder. They are speaking simultaneously, one of them in Korean, the other in Chinese. And let's hear what the microphone hears.
저희가 이 알고리즘을 개발하기 전에 처음으로 정했던 스펙입니다. 이 컨피그레이션에서 여러 가지 많은 테스트를 먼저 행해야 했고
So the question is, can we separate those signals? And after some computations,
都淹水非常严重，有非常多座大桥都断了，并且之后随着之后也有非
and the other channel?
저희가 이 알고리즘을 개발하기 전에 처음으로 정했던 스펙입니다. 이 컨피그레이션에서 여러 가지 많은 테스트를 먼저 행해야 했고
Let me clarify, this is not separation of Korean and Chinese. This is a separation of two sound sources. It works perfectly when the two persons speak English. And this is actually quite compelling. We sit with my wife on the couch. She watches the soaps on the large screen of our TV, and I use picture-in-picture to watch the football game. But I can control with my voice separately what I'm watching. This can save families, people. Yes, heavily. Kinect 1. I know that most of you are not into the audio processing, but if you do, you can learn a little bit more about the audio processing algorithms from my book. And that was pretty much it. We have time for questions. Don't forget that we have a demo in the room when we have the lunch, so feel free to stop by and to ask questions. One last thing, I want to recommend you the talk tomorrow at this time, I think 12 to 1, which is discussing of the natural user interfaces in Kinect. You guys have the floor for questions. Thank you. No questions? Go ahead.
Can you talk a little bit about the APIs and tools that you'll provide with the Kinect SDK when that comes out? Specifically, will there be speech recognition and in those kinds of tools, or is it going to be just raw audio, close to your DSP processing?
So the question is what we provide as a tools for in Kinect for Windows Development Kit. It will come with a driver for the Kinect device. As far as the audio is concerned, which will show us a 4-channel microphone. There will be a processing block packaged as DMO, digital media object, which will do the processing and will output 1 channel, pretty much what we saw in the demo. There will be a recommendation which exactly speech recognizer to download from Microsoft.com and acoustical model trained for that output of the pipeline, sample code. So pretty much end-to-end story. You will be able to build a nice and cool voice-enabled applications using the tools in Kinect for Windows Development Kit. More questions?
Do you expect this to be applicable to mobile devices or smaller devices?
Let me put it in this way. As far as the audio sound capture is concerned, we have done some work, we means Microsoft Research. We discussed this very seriously with our Windows Phone team. Can we provide certain processing blocks in the operating system and work with certain telephone manufacturers, because most probably will need more than 1 microphone, to get this hardware in place so our software can process it. But in general, yes, we really want to have a better sound capturing story. For now, we have a voice search. It's a Bing application. You press speech button. We just record your voice, send it in the cloud. The extremely powerful speech recognizer processes it there and gives you some local shops and etc. local information. We have a pretty decent speech recognizer part of Windows 7 phone. So pretty much the stage is set for building speech-enabled applications in Windows Phone. Maybe they are not going to work when you're on the train station or in the airport, but in a more quiet environment, even today, you can write a pretty decent speech-enabled applications. More questions? Go ahead.
So currently with the Xbox, it doesn't seem to be using speech recognition very extensively. Is that just a matter of people getting used to it and software developers using it?
Actually, so the question is that Xbox does not use extensively speech recognition, and you are correct. I mentioned at the date when we finished the audio pipeline and the speech recognizer training. So most of the game developers got the previous version non-optimized pipeline, so they didn't trust much the speech recognizer. We had just time to put some speech recognition features. It's very shallow. From the moment you go deeper, you have to do gestures or even to get the controller. It's obvious that in the next releases of XDK and the console, we'll see more and more and more speech pretty much everywhere. And we will see more and more speech in the games because the game companies already have the proper audio pipeline, the proper speech recognizer. This effort will continue. This is just the beginning. More questions? Thank you for coming here. Feel free to come by and to see